Hi kids, this is actually the re-recording of chapter 15 because of an unfortunate mute button error. But chapter 15 is about the heart, and we're going to cover these major topics. So we're going to bring up this double circulation, meaning that we've got two different places that we're pumping with our heart, one to the lungs, one to the rest of the body, or systemic. Then we're going to look at the general anatomy of the heart, discuss the number of chambers, which way the blood flows. Then we're going to talk about some of the ways that we measure the activity of the heart in the clinical setting, the EKG or ECG, the electrocardiogram. We're going to cover very briefly how to calculate the heart rate from an EKG chart. And then finally we'll talk about what generates the numbers for another clinical measurement, the blood pressure. So double circulation is a big topic for us. So again, that's about how the four different chambers of the heart pump to two different places. And so the right side of the heart is set up to pump through the lungs, and the left side of the heart is set up to pump through the rest of the body. And we'll cover going through each of the different chambers in the next slide. But just note here that as the unoxygenated blood returns to the heart, gets loaded in the right atrium and then into the right ventricle. The ventricles are the pumping vessels. The reason that you need a decent size, decently strong pumping vessel to get through the lung is because this, remember we covered that in previous chapters, the lung is a huge network of very fine vascular blood vessels. So the major work of pumping isn't about getting through the major vessels like the aorta or vena cava or anything like that. It's actually about pushing through these vessels that are only a cell width or two thick. So if you get fat, the number that they toss out there is every pound of fat adds a mile of vasculature that your heart has to pump through. And so that's one of the major reasons it takes such a heavy toll on your heart. Well, the lung's not terribly different from that because it's all this very fine vasculature, and again, it's a big network of this stuff. So to get through that, we need a decent sized chamber, and that's the right ventricle. It will then return through the pulmonary vein oxygenated. Again, we'll cover the flow again next. But then there's a second chamber of the heart, the ventricle, that's going to be responsible for pushing it out through the rest of the body. And because those two major pumping vessels are not really directly connected, the force from each of those goes through a different system. We call that double circulation. Again, one to the lung, one to the rest of the body. This is just to familiarize you with the external anatomy. Notice there's several different major blood vessels on the top of it, and when you actually have these in hand, they're not going to be terribly distinct from each other because they're just going to be dull gray preserved tissue. So their position is important, especially as you try to trace the chambers leading to the different chambers of the heart. One major thing to point out is the apex. This will be associated with the exterior of the left ventricle, which is the shape about here. Make sure that you can find that so that you can orient yourself. Notice that some major blood vessels that actually service the heart tissue itself run along there. I don't think we're going to get you too bad on the actual names of those blood vessels, but you can take a look now. Note kind of the major ones you hear about, the coronary artery and so forth. Then, let's see. So the major vessels here, the vena cava, that's how the blood returns. The aorta, how it goes out from the left ventricle, and then the pulmonary trunk right here. So this is a great figure for memorizing the blood flow, or for analyzing the blood flow through the heart. So again, remember, it comes in through the vena cava, and that, I should say at the outset, this is something we're going to get you on. Make sure that you can trace it through every structure, every vessel, every valve as they transition to each other. Make sure that you know the multiple names for the different valves too. Tricuspid is the one used in this figure. Instead of bicuspid, they use the mitral valve here in the left ventricle, and I believe those are all in your book. But just for our purposes, just to go over it, let's trace the path of blood. Unoxygenated comes in through the vena cava into the right atrium. The right atrium is kind of a holding chamber for the blood. Once the right ventricle pushes out the previous set of blood, the right atrium will contract, and these contract at opposite times. So the right ventricle is now empty, therefore the right ventricle can now pump. It will push the blood through this valve, which once this is full, the natural impetus of the fluid in there will be to backflow. It will be trying to go this way. But this valve is unidirectional, especially because of the presence of these kind of strings that look like they're the strings on a parachute. They kind of act the same way. They hold this tissue in place so that as it tries to flow this way, because of the blood pushing on it this way, it can't, because these chordae tendineae are actually holding the valves in place. So that's an important anatomical feature. Anyway, now that we're in the right ventricle, we got a fresh batch of blood. The right ventricle can then contract, push it through the pulmonary valve and through the pulmonary artery, where it goes to the lungs and that vast network of vasculature, get oxygenated, and come back, now depicted as red because it's oxygenated, through the pulmonary veins and into the left atrium. Left atrium is similarly a holding area for the blood until it can be squirted into the left ventricle, again through a valve, which prevents backflow through the same means. And then the left ventricle, once that's ready to fire, will push the blood through the aorta and out to the rest of the body. Notice there's some major channels on top here to provide blood for the structures of the head and so forth. That should be those. So there's another anatomical feature that we didn't mention, and that is the apparatus that serves as the pacemaker for the heart. That is, these are a group of cells, of cardiomyocytes, that actually provide the electrical impulses that tell the heart to fire. And again, it's synchronous and it's asynchronous. And what do I mean by that? So the atria, both of those muscles, all the muscles associated with that, contract at the same time. That is asynchronous from the activity of the ventricles. It's completely counter to. So as these are contracting, the ventricles are relaxed. That allows the flow of blood into the ventricles. And then they switch. So once the atria are relaxing, then the ventricles can contract. But that's still a lot of cells that are firing all at once. It's just doing it in two different sets. So they do need somebody to coordinate this. And these are these two major nodes here. The synatrial node here, and then that acts as the primary pacemaker of the heart. But if that doesn't work for some reason, then a secondary node, the atrioventricular node down here, can take over as the pacemaker. But moreover, it's kind of a way station for spreading this electrical impulse from where it originates in the atria up here next to the vena cava. That signal spreads in a web over the atria first. Again, that web covering them all, sending that electrical impulse over that vast area of muscle so that it all contracts at the same time. But then again, it spreads. This all fire, and then this all fires down here in the ventricles. that activity we can measure even through the skin because it's an electrical impulse. And that's what an EKG, or that's the German spelling, electrocardiogram versus the English ECG. That the output that gives you looks something like this. And each of the bumps on the graph represent the electrical activity of the heart at various stages. Remember, with electrical impulses in biological systems, there's depolarization, that's firing, and repolarization, that's getting ready to fire again. And so what's represented by what? So the atria depolarizing, the atria firing, are represented by this P bump up here up front. So they go first. The much bigger activity from the ventricles compressing, contracting, is here in the QRS complex, it's the R. Then the activity from the ventricles repolarizing, is here in the T. So in class we stopped and talked about this for a little bit, but the question was, what's missing? And the answer to that is the atrial repolarization. And so then the question is, where is it? Really, it's just not that major of an activity, and it happens at the time when the ventricles are firing, so it kind of gets lost as noise here in this QRS complex. So one of the things we'll have you do is, if you get a plot of your heartbeats, you want to be able to interpret at least how quickly your heart is beating. And for that, it really is as simple as finding out how many beats happen in a given interval, and then since we want to convert it to beats per minute, we have to convert the interval that we had to 1 minute. So in this example, we're given an electrocardiogram where there's a fraction, we'll keep that in mind, and then 1 beat, 2 beats, 3 beats, and then another little fraction here in an interval that we're told is 3 seconds. So when we kind of analyze that a little further, we determine that it is 3.75 cycles, beats, in 3 seconds, which if you wanted it per second, here's that calculation, you just divide. But normally we report this in minutes, or beats per minute. So we actually multiply that by 60 seconds to get us to 75 beats. If you want to cancel everything at the same time, you just put all the different conversion factors into one equation and get the same thing. If you're given a chart like this, what will be important to be able to figure out is you need to be able to count how many boxes there are. And then there should be a given table for how big a box is. So each one of these together, we're told, is 1/5 of a second. So that's a big box denoted by the grid here, and every tiny box is 4/100ths of a second. So if you add all those up, you should get to 3 seconds for this interval here. Moreover, you need to be able to make sure that you count the number of intervals correctly. If you counted 1, 2, 3, and 4 within this interval, you'd be incorrect because you need a starting point of some point. So really it's 1, 2, 3, and then 2 pieces of a cycle here on either end. So don't just count peaks, count the intervals. Finally, we'll also talk about another diagnostic, blood pressure. That is how much pumping your heart has to do to get it through your body. So the systolic value, it corresponds to the amount of pressure generated when your left ventricle compresses and tries to push all that blood out to the system. That's when your blood flow is meeting the maximum resistance. So gradually that decays because there's still an inherent tension. It's still flowing through your body, even if your heart isn't contracting at that moment, or rather if your ventricles aren't contracting at that moment. And that value, that persistent pressure in the system, is the diastolic value. If you think about how this is actually measured, you put a pressurized cuff around your arm, and you say, how much pressure do I need to apply from the outside to block the blood vessels from letting the blood go through to the arm? And so, and then the other thing you measure is how much pressure do I need to apply before that blood can just ambiently flow backwards and return to the system through the veins. And those respectively are the systolic and the diastolic. So it's going to take a lot of pressure relatively to stop the blood from going out. Remember, the greatest pressure is from when your heart is pumping through the left ventricle. So when that is happening, you're going to need, for a good healthy individual, about 120 millimeters mercury to get past pressure in the cuff to stop the blood from going through to the arm. And again, in a good healthy person, you might need only about 80 millimeters mercury to prevent the blood from flowing back through the arm without the major push of the blood of the heart. Sorry.